particle or it doesn't. It alternates, and it's all nicely fit together. And again, I should be finished, and it would be wise to stop. But perhaps you'd like to see a little more general detail about how that sign comes about in a more clear fashion. And so what I would like now to write is the general rule that connects the particle and antiparticle. We said it quite clearly that you look at it backwards. To be more precise, the following is true. An antiparticle going from an initial state of momentum pi and energy ei in a certain particular spin state ui, even if it's not spin a half, whatever spin it is, spin 1, whatever, 0, that's no spin. Starting in that state, and do various things. For example, it could emit a photon of polarization A. I just made a little example of the momentum q, energy omega, to end up in a state of momentum pf, that's this one, with its energy ef, and with another spin uf. This happens with the same amplitude that a particle does something. And you just have to do the particle by looking backwards. Right? The particle starts in a state of momentum pf, ef, and the spin, which is a reverse, the pt, reversal of uf. Actually, the p isn't going to make any difference, but just mainly the time reversal of the spin. It absorbs a photon of polarization, it comes out minus a star. I'll explain why. Momentum qa. It has to be a star because when you emit over here, you have the coupling a star, but you're going to talk about absorbing it. Why? Because the momentum is going the other way. You see, it's picked it up instead of dropped it out. And so it's an absorption instead of an emission, which is time reversal, okay? In other words, it's time reversed, and it's to end up in a state of momentum pi-ei, and here's the key, and the spin state, the inverse of pt times ui. Why is it the inverse? Because in this first thing, we're turning one way, and then the second one the other way. So if we made a pt turn this way, and then we make an un-pt turn. In other words, one's a time reversal, and the other's the inverse of a time reversal. Sounds the same, doesn't it? All right, we'll come back to that in a minute. As a matter of, just let me make some notes here first. First, if I had an object of momentum p, the time reverse state would have momentum minus p, huh? Right. But then if I use a parity that I changed all the axes, the minus p would be flipped back to p. So that's why it's still the same momentum. In other words, what we're doing here is the c that is changing from particle to antiparticle is equivalent to parity change and time change. Everything is done in the reverse order in time. And if you work out the time reversed polarization, you discover, for instance, if you had circularly polarized light with the electric field going around one way, you have Ex equal 1 and Ey equal I. If you take the complex conjugate of it, it goes around the other way, the electric vector, and that's the time reversal and so on. So everything just fits together to make this exactly the statement that this is what's happening. Instead of particle antiparticle, that's the C, but everything backwards in time and everything reversed in space. And I'm not going to go into details to prove it any further. Now, the little difficulty is that here we have a state pt ui, and here we have pt to the minus 1 ui. I mean uf, and here's pt to the minus 1 ui. Later on, we'll want to go from a state to the same state. So it's much better to have the same system. So if I had a state ui to going ui, I want to have pt ui to pt ui. So I'm going to change this pt to the minus 1 ui to pt ui because I'm going to show that for spin and a half, see, if the states are the same, the in and out states are the same, then we can check the signs of the real parts very easily because they were the same previously. However, for spin and a half, I'm going to show you that pt reverse, negative, inverse, is the same as minus pt. In other words, by the way, you can choose the p phase the way you want, but let's choose it so that p squared is 1, so there's no problem with the inverse p equals p. So what we're going to show t to the minus 1 equal t minus t multiplied by t means we're going to show that t squared is minus 1 for spin 1/2 and plus 1 for spin 0. And when I change this to pt, I have an extra minus sign for spin 1/2, and that's where it all comes from. Why should it be that the sign, that changing around t twice changes the sign of spin 1/2? Because a 360-degree rotation changes the sign. And if you can think in space-time, huh? Foink, foink. T twice, right? Turn it around twice. It should be 360 degrees. Oh, yeah, in some crazy XZT space, but smells right, doesn't it? I mean, if I flip the x-axis twice, I would be rotating 360 degrees. Maybe it's true of the t-axis, too. And that's what I want to prove. I want to prove now that it's true that if you make a time reversal twice on a spin 1/2 particle, you get the same state with a minus sign. In other words, 2 t's is the same as a 360-degree rotation and changes the sign. That's where it all comes from. This is, in fact, so elementary, and it should be an elementary physics textbook because it's so much fun. Having to do with time reversal. I have here a list of states, and here they're time reversed states, and here they are twice reversed. Let us call a state A. The state might be a particle doing this. No, that's too complicated. Particle doing that. And then the state TA is a particle doing this, okay? Or a particle with momentum this way would be A. Then the TA is a particle with momentum that way. All right? So TA means, this is Dirac's notation, okay? And this is the name of the state. And what I mean by this is simply the name of the state. I'm describing the name of the state, the time reversed state. For instance, a particle, and if I do it twice, I get that. A particle located at x, time reversed, is still located at x, no big deal. So this is this. A particle of momentum p, we just said, was a particle of momentum minus p when you reverse it. So, but a particle of momentum p can be made by the superposition of particles at different x with the phases as given. The minus p would be with the opposite phase. And so we discover that time reversal is what's called an anti-unitary operation. You must take the complex conjugate of the coefficients whenever you see them. For instance, if there's a state alpha A plus beta B, a superposition with coefficients that need not be real, then the time reverse state is alpha star times the time reverse state of A plus beta star times the time reverse state of B. And that's the general principle of time reversal. Now, if I could take the time reversal again, with x, it goes to x with minus p. Change the sign again, it's p, so that's okay. Nothing happened there. And with this one, it's alpha times TTA plus beta TTB. Why? Because I take the complex conjugate twice, and if you're very good at algebra, you know doing that is a waste of time. Now this state, of course, being twice time reversed must be the same state again. It's, you know, like a 360-degree rotation. You do it twice, it's the same physical state. And the damn quantum mechanics always permits you to have a different phase. So you can't say that this thing is the same state as that, but you can say that this thing is a phase times that. And that means that TTA is e to the I phi, that is, I wrote badly, a phase times A, e to the I phi times A. And all the states have the same phase, so that this interference that I have here will be the same interference there. So there's a universal phase shift when you take double time shift. Now let's look at spin. A half. Let's take the state which is spinning up in the z direction. Well, first let's talk about spin. It's spinning. What's the time reverse? Spinning the other way. All the spins have to be reversed. Every state goes into the opposite physical state. Let's start with the state up in the z direction. It'll go into the physical state down in the z direction with some phase. It's easy to prove that this, you can start with any phase and it all comes out the same in the end. This phase I'll choose to be 1. So it just comes out that the time reversal of the up spin is the down spin. Yeah. Now the time reversal of the negative z spin is a phase times the positive z spin, of course. And we're going to show that the phase must be negative in just one moment. Because let us consider the linear combination, which is plus and minus. This should have been plus z and minus z if I wrote that out so carefully. If you superpose equally this one and this one, you'll get the state representing positive x. If you do them with opposite sign, you get the state negative x. All that should be known to the elementary student of spin. Now let me suppose that I try to say that the time inversion of minus z is the state plus z without that minus sign. Then do you see that the time reversal of the state plus x, this plus will go to minus and this minus will go to plus, will produce the same state again, which is not right. It's supposed to produce the opposite state. And therefore I have to change the sign here. Otherwise, when I did the time reversal, I would produce the same state. Well, if you put the minus sign in there and watch what happens, the plus goes to minus and the minus goes to minus plus. If you can understand such a horrible thing. And if you look at it a bit, you'll find that that's the negative of the spin in the minus x direction, and that's what the negative is, just a phase, and the spin in the minus x direction is what we want to reverse. Hence, it's necessary with spin a half that if the time reversal of the plus state, up state, is the down state, that the time reversal of the down state is minus the up state. It's so much fun. Now we do it again, huh? Well, we just learned that the time reversal of the down state was minus the up state. And here we learn that the time reversal of the up state is the down state. Now to keep this minus sign going through. So you see that if we do two time reversals, we change the sign. So it's just necessary, and there's nothing, it wasn't in space, but we did it, two reversals of spin, two time reversals, and you change the sign. It's equivalent to, it's just what you would do if you rotated 360 degrees. For a particle of even spin, which can have a state with a component along the z-axis of 0, the time reversal of that is still 0 along the z-axis. Any positive spin will turn negative, but the 0 will be 0. So therefore, the time reversal of this state, some j that's even, I mean integral, with the m equals 0, will be some phase times the state with the m equals 0. But if you do the time reversal again, I got the time reversal of this is e to the minus I phi times the time reversal of that, because of this alpha star. But the time reversal of that is e to the I phi, and these phi's cancel out, and you get the j m equals 0. So therefore, 2 t's on a integral spin is plus 1. In other words, 2 t's has the same effect as a 360-degree rotation. Okay. It's minus for spins a half integral spin, and it's plus for integral spin. How did I get here so fast? Okay, then I got them in the wrong order. Nope. Now when we look at the sign of a loop, I'm going to talk about the loop that had the contribution that was supposed to stop the vacuum. You remember, if you have a potential present, you can produce pairs. Therefore, the probability that you don't produce pairs must be less than 1. And you have to get the sign of the loop right so that 1 plus those loops is less than 1. In other words, the real part of the loops must be negative. And what you have to do that is when you have Bose, you have two particles coming out and going back into the same state. You have to have exactly the same thing with the positron and the electron going out and coming back in the same state, as indicated here. And I've written it out more carefully here. The amplitude is 1 plus x, where x is the contribution from this loop. Its real part times 2 must be negative and cancel the probability of pairs are produced, so that the sum of the probabilities over all alternatives remains unity. And that's going to determine the size of the thing. Now, to get the sign of the positron propagation to be right, just like a particle going from a state to the same state, we saw that we have to multiply by an extra tt. Otherwise, we'll have the wrong contribution of positron, have that extra minus sign. In other words, we have to multiply by minus 1. That is, the x is the loop trace times minus 1.